Hi, hello, good evening, everybody. Welcome to the Astro Imaging channel. This is Molly, and I'm hosting tonight. Tonight we have one of our own, Tim Hutchison. It will be giving tonight's presentation about dealing with noise in astro images, something we all universally deal with no matter what level of the hobby you're at. Real quick, I'm not going to pull up my screen, but let me just run through our upcoming shows on the calendar. Next week, we have Ron Brecher on to come talk about doing processing with the stars extracted from the image, which is really easy to do now with StarNet or with Star Exterminator. We're not having a show on Father's Day, June 16th. And then June 23rd, we're having our 10th anniversary show. And so we're going to do a little recap of the year, talk about how things are going on YouTube, and also do a couple of shorts like we've done in the past with some of us getting on and giving short form presentations on particular astrophotography topics. So we got some exciting stuff coming up and also a bit of a break. Anything else to talk about? I don't think so. All right, Tim, take it away.
Okay. Hi, everybody. Good to be here again. I'm going to start sharing my screen here and we'll get rolling. So let's do that. Let's do this. Somebody give me an okay that you can see that and we'll get moving.
Yeah, looks good.
Okay, great. So I think, you know, if you're a regular on the channel, you've heard me speak before. My name is Tim. I'm a retired CEO of a software company. I started as a landscape photographer back when I was in my 20s as a much younger man. And I started in astrophotography in 2018. I currently have a telescope out at the SRO. That's the one that you see pictured there. I also have an observatory in my backyard where I have a TOA 130 or I swap it out with my solar imaging rig. So that's just a smidgen about me. What are we going to talk about tonight? You don't care about who I am. What are we going to talk about? So you know, Alex came around with some suggestions for things that we should be talking about not too long ago that he plucked out of, I think, Cloudy Nights and some of the other boards that he was looking at. And one of them was, you know, a bunch of questions about noise and what noise is. And so I thought it would be a great topic for us to talk about tonight and discuss what noise is and what signal is, discuss the different types of noise and signal and what they are and where they come from and, you know, how we work with them, discuss what we can do to combat those you know, bits of noise that we deal with and the unwanted signals that we deal with to get down to the wanted, to the desired signal that we have, which is our target object. And then I thought we'd end with how we might be able to use our cameras more efficiently to kind of reduce the noise or to work with the noise that we have out there. We're not going to be talking about noise reduction like using programs like Blur Exterminator and things like that. You know, that's I think pretty obvious to all of us, but I think there's sometimes some confusion in what we're talking about when it comes to noise and signal and what we're actually dealing with. So that's what we're going to chat about tonight. Why do we care? Well, that's the first issue, right? Why do we care about noise? Well, simply put, noise obscures the fine detail in our images, right? So you see up at the top, what I have here are 1, 2, 3, 4, 5 little circles, and the smallest one is, you know, down here at the far left-hand side. And you can see I've just added noise to this image. You can see that as the noise increases, this small circle just goes away completely, right? And as the noise gets greater and greater, even this little larger circle and the roundness of this circle start to fade away. So this is why we care about noise. Even if we had this image at the bottom and we did some noise reduction, we would never recover this detail that we have in the first image. And that's why we care about noise and why we want to try and reduce noise in the images that we take, even though we have great things like Blur Exterminator and TGVD noise and all these other great tools that are out there. They'll never recover this detail if we lose them to noise. And so this is why we care. This is why, you know, we want to think about noise during the process of gathering our data, during the process of collecting our images, not just at the end when we can throw some noise reduction at it. So this is why we care. This is why we want to think about this kind of stuff. So let's talk about what is noise and what is signal. Signal, simply put, is the response that we get off of the sensor, right? When we detect something from the sensor will give us a response that's proportional to the energy that it detected. That's signal. Now, there's good signal and there's not so good signal, and we're going to talk about that in a minute. Noise, however, is the random contribution from lots of different places, from various different sources that affect the measurement of that signal, right? Noise gets in there and messes around with what it is that we're really trying to measure, okay? Signal to noise ratio, I know we throw this term around a lot, but you know, we should really understand that signal to noise ratio really is a measurement of how well we're measuring the signal that that's what SNR really is to us, is a measurement of how well we're capturing that original signal. Okay. So what are the different types of signal that we have out there? Well, the obvious one is the signal from the target object, right? Photons that have traveled cosmos and impacted our objective, impacted our sensor, and we're trying to measure. This is the good stuff. That's the stuff that we're looking for, is the target object signal. That's what we want. But there are other pieces of signal out there. Like, for example, there's thermal signal. Thermal signal is an unwanted signal. It gets in the way of what we're trying to do, but it is signal. We're going to talk about what thermal signal is, what all of these are in greater detail, but we're just going to mention them right now. So thermal signal is one of the other types of signal that gets intermixed with our signal from the target object. We have signal from air glow, the faint glow that appears in our atmosphere, that gets in there, interferes with the target object signal that we're trying to collect. Stray light, obvious one, right? Light pollution, obvious one. Cosmic rays, another obvious one. These are all things that are measured by the sensor and show up as signal in the images that we're trying to process. Okay. Lots of different types of noise that we deal with. There's shot noise, read noise, hot and cold pixels, fixed pattern noise. There's a couple different types of that. And walking noise, which is really a manifestation of fixed pattern noise, but I threw it in there just so that we talk about it separately. We're going to talk about what all these are, where they come from, and what we can do about each one of them as we continue on tonight. So this is what we're going to be talking about. All right, so if I am an electrical engineer, this is where I live and breathe. I'm going to try and not to get too electrical and engineering on you all, but it is important that we understand a little bit about what we're talking about on the sensor so that we can understand where some of this noise is coming from. Okay, and the first thing that we need to understand is that our sensor is made up of something called a photodiode. Now, for the electrical engineers out there in the room, a photodiode is a PN junction. That's a piece of silicon that has what's called a depletion region in the middle that reacts to photons. The rest of us don't care. The only thing that we care about is that when photons impact this photodiode, they cause the electrons that are in this thing called a depletion region to become excited. And they jump from, if we remember our chemistry, from the valence band in that silicon atom, electrons jump from the valence band up to the conduction band. And when they do that, when they get excited like that, it induces current in this photodiode. It makes current flow. That current gets amplified in a circuit like what we see. Let me get myself a little pointer here. Where's my little pointer? I don't remember how to do that. Can you see my cursor? Somebody tell me if you can see my cursor here.
Yeah, it's a little small.
Yes, a little small.
I think if you hit the three dots button, that might be where you're.
Three dots.
And then, pointer options.
Pointer options. Thanks, Molly. Visible. Okay, there we go.
Well, I was hoping for the laser pointer.
That didn't help us. Anyway, all right. So this little thing with the orange triangle in there, this is an amplifier circuit. We don't really care how they work. But what we need to understand is that when this photodiode, when we induce current in this photodiode by photons of light hitting it, it creates a voltage, right? And we're talking about CMOS sensors here. I thought I would limit my conversation to CMOS sensors because, CCD sensors are are not as popular anymore, and most of the things that I talk about are going to have a parallel when we're talking about CCD, but primarily tonight I'm going to be talking about CMOS. So in any event, when we have this photodiode that creates an output current, we turn it into voltage with what's shown as an orange triangle here, what's shown as a green triangle in this array of pixels that we see over on the far right. And that output voltage gets sent down to this big green triangle that we have here in the bottom right, which is where our what's called our output amplifier is, that gains the signal up. This is where our gain comes in on our CMOS sensor. It amplifies that signal. We convert it from analog to digital with this thing called an analog to digital converter, an ADC. And at the end, we have our digital output. So there's a lot of electronics here that goes from this photodiode, this thing that reacts to light, and we turn it into a digital signal on the end. So we just want to really keep in mind that we have these three circuits here. We have the amplifier on the pixel, we have the output amplifier, and the analog to digital converter. And that's really all we need to learn from this slide. I thought it might be interesting for you to also see the difference between what's called a front side illuminated sensor and a backside illuminated sensor, since that's kind of in vogue right now. You know, Sony's sensors, the IMX, what is it, 455 and whatever other ones that they have, they're all backside illuminated sensors. And why is it important, or why are they different, or why are they better? The reason that they're better is because of the construction. And so let's talk about this construction just a little bit. On the front of each pixel, we have this piece of glass that you see here, this little bubble that you see at the top, that's called a micro lens. And this micro lens kind of gathers the light and focuses it down to the photodiode. If we're talking about a color sensor, either a DSLR, a mirrorless camera, or a color astrophotography camera, they'll have this Bayer matrix in here, and that's what this red, green, and blue section is that Bayer matrix, those color filters. If it's mono, that wouldn't exist at all. But this is the important bit right here in the middle of the front side illuminated sensor that we see on the left, where all of this wiring and circuitry is in this kind of orange area. This is the difference between a front side illuminated sensor and a backside illuminated sensor. And it used to be that this wiring and circuitry, or all these little amplifiers and stuff that we just talked about, it used to live between the micro lens and the photodiode. And the problem with that is that some photons would come through and that ping off of the metal and all the stuff that's in this wiring and circuitry layer and bounce out, and they'd never touch the photodiode, right? And the reason that the quantum efficiency is so much higher in the newer sensors is because they've taken this wiring and circuitry and flipped it around to the back of the sensor, right? And so this stuff is now flipped over to the other side. The photons of light have a clear path from the micro lens right into the photodiode, and nothing is getting in the way. Nothing is causing those photons to bounce off and bounce out of the way. So this really doesn't enter into our discussion of noise, but I just thought it might be interesting for us to understand the construction of the silicon a little bit, and why the backside illuminated sensors have a greater quantum efficiency, why they are seem to be the direction that that production is taking when we're talking about CMOS sensors nowadays. Okay, I hope that makes sense. And if there's questions, Eric, feel free to just jump in. If people are typing, what the hell's he talking about, in the comments, just feel free to jump in and interrupt me when necessary.
No question
Okay.
yet, but I will.
So anyway, that's what we need to know about the sensor, is that we have some electronics on the pixel and in the output amplifier and in the analog to digital converter. And that's all we need to remember for right now. Now, incidentally, if we were talking about CCD sensors, the real big difference is that we don't have these electrons on each pixel. They have one row amplifier and one output amplifier, and that's it. That's really the big difference between the two, is that they don't have each of these little green triangles that we see on each of these pixels. That output, that amplifier there, doesn't exist on each individual pixel. That's really the big difference. But anyway, we're not going to talk about that. Okay. So let's talk about signal from photons, right? We talked about here in the photodiode how photons come in, impact this, depletion region, this thing that I'm calling depletion region. The photons come in, smack into that, and it causes signal, right? It causes an excited state of electrons that makes current in the photodiode. What is it that's causing that signal? Well, there's lots of things. There's photons from the target object. We know that. We also get photons from air glow. If we're we're experiencing air glow, that's light. That's photons that are going to impact that photodiode as well. We have stray light. If we have stray light coming in from a street light or what have you, your neighbor's porch light, or reflections in our telescope, we have stray light that'll cause signal there. Light pollution is one that we're going to spend some time talking about tonight, but the light pollution causes a certain number of photons to impact that sensor. And cosmic rays, right? All of these are examples of photons from the outside world smacking into that photodiode and causing current, right? Incidentally, I should mention, and I'm just going to back up for 1 second. We talk about electrons a lot, and you're going to hear me talking about electrons. And where does that whole thing come from? Well, all of that happens right here in the photodiode. When a photon comes in and smacks into this depletion region, it excites these electrons and they jump up to a different level of energy and they cause current to be in the photodiode. So we talk about electrons when really what we're talking about is photons. And there's a proportional relationship between the number of photons that impact the depletion region and the number of electrons. So we're going to be saying electrons a lot, but understand that there's a proportional relationship between those electrons and the photons that actually have impacted our sensor. Okay. All right. So the one bit of signal that we left out in this previous slide that I told you was signal before is this stuff called thermal signal, or it's often called dark current. Same stuff, right? We're talking about the same thing. And really what we're talking about here is heat that occurs in this sensor has the same effect as a photon impacting the sensor, in that the heat will excite the electrons in the same way that a photon does. And there's a small amount of current, and you see in my second statement there, even in the absence of incident light, in other words, no photons impacting the sensor, there's a small amount of current that's produced by the photodiode from thermally generated minority charge carriers in the PN region. Who cares what that means? What it really means is there's a little tiny bit of current that gets generated in the photodiode just because it gets hot. And it looks exactly like it would if light was impacting that sensor, right? Albeit smaller, okay? The magnitude of that current is related to the temperature of the sensor. So the hotter the sensor gets, the more current we have, right? Now we have to remember that this dark current that we're talking about, this thermal signal, is signal. It's not noise. And myself included, a lot of us fall into the trap of talking about this like it's noise, but it isn't noise. And the reason that I'm going to make a distinction there and call it signal and try and be very good tonight about calling it signal is because it's susceptible to all of the other pieces of noise that we're going to talk about tonight, including most significantly read noise and dark signal non-uniformity, which is a type of fixed pattern noise. We're going to talk about that in a minute. So this thermal signal that we have is susceptible to all of those other pieces of noise, just like the signal from our target object that's coming in as photons and impacting the sensor. So that's why we have to remember to think about our dark current as signal and not as noise. Okay. All right. So let's talk about dark current. It's specified by the camera manufacturer, usually in a graph that looks something like I've shown here. And I just grabbed two examples that were out there, on the internet, the ASI 290 and the QHY 600. These are just two different chips, which is why I grabbed these two. But they both kind of are structured in the same way. And what we're showing here on the x-axis, you notice, is the temperature of the sensor. And on the y-axis, we have the number of electrons per second per pixel that's going to be induced into that photodiode, as the temperature of the sensor changes, right? And so you can see here for the ASI 290, for example, that at 0 degrees C, we have around 0.017 or 0.02 electrons per second per pixel that gets induced into that photodiode, right? And that's what we're looking at here. If we look at the QHY 600 around 0C, we have 0.015 electrons per second per pixel that get induced in there as current that we're going to pick up as signal when we read our image, right? So that's what these graphs mean that you get from the manufacturer, is how much current we're going to induce in the in our sensor, in the photodiode, as the temperature changes in the sensor. Okay, now this will become important as we continue on our conversation tonight. Let's talk about light pollution for a second. And I have these two next to each other for a reason. Light pollution increases the base signal in our sensor by a specific amount. And what I did here in this slide is I used stellarium to simulate a Bortle 1 through a Bortle 8 sky. And I don't know how well it's coming out on YouTube. I hope it's coming out well. But over here on Bortle 1, we can see, not only do we see detail here in the Milky Way and lots of faint stars, but also up here where there's no Milky Way, we can see a very black, very dark sky. And as we move across and we go farther and farther towards Bortle 8 here on the other far side, on the right-hand side, we see that our image has gotten much brighter, right? Because it's brighter, we no longer see the detail from the Milky Way. We no longer see faint stars. But what does that brightness really mean, right? What's really going on here? Well, we have a certain amount of light that's impacting the sensor, and we're adding a certain number of electrons per pixel per second into our image, right? Because we have that incident light coming from light pollution that's impacting our sensor, right? And it's obscuring our thermal signal, of course, but it's also elevating our base signal by a certain amount. Sounds a whole lot like what we talked about with dark current here, doesn't it? That the dark current is going to elevate our base signal because we have a certain number of electrons that are being added into every pixel for every frame that we take. So there's a real interesting little correlation here between dark current and light pollution or sky brightness that we can see. Now, if you go out to tools.sharpcap.co.uk, they have a really nifty little tool where we can say, look, I'm going to key in my Bortle. Whoops, I'm sorry. Let me go back. I'm going to key in my Bortle number and the F ratio of my scope and how big my pixels are and the quantum efficiency of my camera. And you tell me how many electrons per pixel per second I should expect in my imaging rig, right? And I thought this was pretty cool. And so I went and I mapped out a little chart here where I took scopes from F2 up to F10. I just took a couple of stops there along the way. And I took skies from Bortle 1 to Bortle 7. And I ran through this little web page and calculated out the signal that we would get with the 3.76 micron pixel, which is, most of these CMOS sensors are today. And I took a 50% QE average across the entire, 300 nanometers for luminance. It may be higher, maybe lower for your camera. This is just an example. We don't have to get into what into the gnat's eyelash or what the values are, but it gives us a nifty idea of the number of electrons per pixel per second that we should see in sky brightness. Now, I personally have a telescope, as I mentioned before, out at the SRO. Our skies there are around an F2, around a Bortle 2. I have an F8 scope. So I kind of sit right here at this 0.25 electrons per pixel per second in my rig. Okay. Now, why do I care? Or why am I talking to you about this? Well, for the next example that I'm going to show you, let's also take a look here. Let's say that we're in an urban sky or a suburban sky. Maybe we're around Bortle 4, Bortle 5, something like that, and an f5.6 scope. You know, a Bortle 4 and f5.6, we've got 1 electron per pixel per second that's coming into our sensor just based on sky brightness, right? Now, why am I talking about this? Why do we care? Well, this is why we care. You know, all of us that are using a cooled astrophotography camera, you know, we cool that camera down to try and lower the dark current that we talked about earlier, right? But if we have, in my case, 0.25 electrons per pixel per second coming in just from sky brightness, right? If I take 1/10 of that, I cut that sucker, you know, down by, you know, divide it by 10, I have, you know, 0.025. And if this is my curve for the sensor that I have, right? Why am I cooling down beyond this point? Why am I cooling that sensor down beyond around, you know, what is this, 3 degrees, 2 or 3 degrees C? It really doesn't make any sense for me to push this sucker down to -20, because you can see that I already have this much noise, this 0.25 electrons per pixel per second coming into my sensor anyway. So that is so much higher than the dark current that I have that it really makes no sense for me to cool this thing down to -20. I can cool it to 0 and be well below 10% of what my sky brightness is anyway. So there's really not a good reason for me to push this sucker down to the frosty limits of what I can do with this, with the tech on the camera, because it's not affecting my image anyway, right? Not in any way that I can see. Further, you know, if we go back and look here, let's say we are this guy that's sitting in Bortle 4 with an f5.6 camera, and we have 1 electron per pixel coming in. Well, you know, you take 1/10 of that, and that's 0.1. So really, I don't have to cool this thing down below 10 degrees for that guy, right? There's no reason for it, because it's an insignificant number when compared to the sky brightness. If I'm worse than that, if I'm somebody that's sitting out here in Bortle 5 with an f2 scope, and I have 21 electrons per pixel per second coming into my telescope, whoops, why do I cool it at all, right? Cool that sucker to 15, and I'm still way below anything that's happening with sky brightness. So just a little aside here, just something interesting to think about, you know, especially if you're dealing with an imaging rig where you're running on battery and you're cooling a camera and you want to preserve all the power that you can. Do you really need to cool this sucker down to -20, -30 degrees? I submit to you, no, you do not. It's not impacting your image. So just something neat to think about there. Okay. So now we're going to talk about read noise. Read noise, I think, is often confused when we're talking about astrophotography cameras and how our cameras work. What is read noise? Well, you know, you remember, if I go back to our little discussion of the sensor here, we had all these little bits of electronics that are between our photodiode and our output signal, right? We've got all these little amplifiers that are in here, and this analog to digital converter, which we're going to talk about what that is a little bit too. But all of those things are in the way of our output signal, that are in between our photodiode and our output signal, right? Read noise is the error that gets induced into our readings of the photodiode from all of those little bits of electronics that are in the way, right? Electronics are not perfect, right? Nothing that we can create out of silicon is going to be perfect. And so there's going to be little tiny bits of random error that occur during the amplification process and the analog to digital conversion process. I raise my hand. Tim, what's analog to digital conversion? Okay, so let's think about this. We have a voltage that might be, maybe it's 0.1 volts or 0.15 volts or 0.2 volts or 0.5 volts or 1 volt, right? That's an analog value, right? It has infinite resolution, and it's a measure of magnitude, right? The analog to digital conversion process takes that analog number, that 0.1 or 0.2 volts, and turns it into a digital number. It converts from this infinite resolution magnitude-based value into a defined, definite representation of ones and zeros that is a physical number. That's what analog to digital conversion is. So it's not mysterious at all. It's just this thing with infinite resolution and turning it into a fixed number on a scale from, let's say we have a 16-bit sensor on a scale from 0 to 65,535, right? That's the range for 16-bit, from 0 to 65,535. And so we take this value that might go from, I don't know, 0 to 1 volt, and we convert that to a scale of a number from 0 to 65,535. That's what analog to digital conversion is, right? And it's not perfect. The amplification isn't perfect. The analog to digital conversion process isn't perfect. And that imperfection is what we refer to as read noise, right? Now, read noise happens in every single exposure that we take, whether it be a light, from our target object, a dark frame that we capture when we're capturing darks, a flat frame when we're reading flats. We always have read noise, right? It doesn't depend on exposure time or temperature or anything like that, but you pay a fixed price for read noise on every single subframe that you take from sensor to an image file, right? Now, the manufacturers typically publish a graph or a chart like this. And again, I've chosen a couple of samples that show the change in read noise with the gain of the sensor. Now, in CMOS cameras, if we think back, we had that one little green triangle that I had down on the bottom right-hand side. If you remember, that one little green triangle had a gain input into it. That gain is how much we're increasing that voltage before we take that analog signal and turn it into a digital number. And that gain impacts our read noise. Typically, as the gain goes up, the read noise goes down, right? That's true of both CMOS and CCD cameras. As the gain goes up, the read noise goes down. The difference is, in CCD cameras, we weren't always in control of the gain. In fact, with most, we were not in control of the gain. The gain was fixed and set by the manufacturer. Whereas in CMOS, we are in control. We can play around with that number. But anyway, and let's just look at these first three dots here of the ASI 6200 and the first four of the 294. We see that as our gain goes up, this read noise is dropping. Now, the big question comes in, why do we have this big avalanche? Why is there this big change right here at gain 100 on the ASI 6200 or at gain 120 on the ASI 294? What's that all about? Why does it change so rapidly? Well, the reason is, and my drawing that I showed you earlier was a little bit simplified. They have two different circuits in there that do this amplification and analog to digital conversion process. They switch right here at 100 on the 6200 or at 120 on the 294 from what they call a low gain amplifier to a high gain amplifier. And as soon as that switch occurs, all of a sudden we have different properties. And so that's why we have this big drop in read noise from what we have from a gain of 0 up to 100 on the 6200, and then from 100 all the way out to its maximum, right? That's what this big drop off here is that switch from their, what they call their low gain amplifier to their high gain amplifier. They just have different properties, right? Frequently, folks choose a spot after this drop off benefit from that lower read noise with a little increased gain. We're going to talk about this tonight, and I'm going to show you why it might not matter so much. But that is a common thing for us to do, is say, well, if I'm shooting with a 6200, I want to be at gain 100, so I benefit from that lower read noise. Okay.
Tim?
I know this is a confusing subject, so I'm not surprised you interrupted me there. Let's go ahead.
No, there are a couple of questions that come up. Let me see if I can read them for you. Okay, wouldn't the analog value not be perfectly continuous since you can only have an integral number of electrons?
Well, that is true. That is true. When I was speaking of, where was I? I was back here. When I was speaking of that, that analog signal being, infinitely, infinitely fine. That's true of analog signals in general. Now, here, you're right. We have a finite number of photons that are impacting the cells. So this voltage signal will step based on the number of photons that impact it. But remember, the number of photons, the number of electrons, rather, that get excited by a photon is not 1-to-1, right? So it's not always one electron for one photon. That's not what happens. We don't need to get into the properties, the physical properties of the silicon, but just know that it's not one electron that gets excited for every photon that hits the thing. Okay.
Okay, next question. Josh says, need to cool down to -25 if the ambient temperature is below any other controllable temperature. I'm not sure what that means.
Well, I've just shown you, John, that really the cooling of the camera is not dependent on temperature. We want to maintain, and we're going to see why a little later, we want to maintain a consistent temperature on that piece of silicon, but we don't have to cool down based on ambient. We need to cool down and maintain a consistent temperature based on what our light pollution rate is, right? So as long as, and I guess what John's trying to say is, well, if it's 5 degrees outside, we need to cool down below 5 degrees, or if it's 0 degrees, we need to cool down below 0. I understand where he's coming from on that. I don't know how many of us are out there imaging that, much below those numbers. But I guess I can understand the point that John's making, is that if we cool down below ambient, we're going to make sure that we have a consistent value out there. But what my point was is that there's really no reason to push this thing down here to -20 when it's not having any kind of positive impact on our image.
Okay, that was actually from Josh.
Josh, excuse me, Josh. I thought you said John. Sorry.
No, I might have. Don't some cameras allow you to make the switch at any gain value?
If that's true, I don't know of it, but that may well be true. I don't pretend to be an expert in every camera that's out there.
And Tariq says, I live in hot climates, so I try to keep my cooling down to between 0 and -10 maximum all year long.
Yeah, and so Tariq, I don't know what sensor you're using, but I think we've shown here that this is a Bortle 2 sky. If you were in Bortle 1, it would be a little bit lower. But if you're down here between 0 and -10 on this particular sensor, you're well below the impact of sky brightness on your image, and the thermal signal at this point, the dark current, is not having a significant impact on your image.
I think that's a question you're probably going to cover a little bit about banding noise. You want to hold that?
Yeah, let's hold that. We are going to talk about that, Isaac.
I think that's all for now.
Good
Molly,
for now?
trying to answer some of the questions online.
Okay, cool. Thanks, Mo. All right, so we're through read noise, right? And we see, and let's keep these numbers in mind. For this particular CMOS sensor, we're somewhere around based on where your gain is, we're somewhere around 3 electrons or 1.5 electrons. And this one, we're around, 1.5 or as high as 7. Let's kind of keep those numbers in mind as we move forward here, because we're going to talk about some other stuff. Let's talk about the big guy. The big guy is shot noise. And I think there's probably a lot of confusion out there on what shot noise really is. And shot noise, to me, is best explained this way, and I've seen it explained this way in a bunch of different places out on the internet. Think of an array of buckets out there on your sidewalk in a light rain. While this light rain is happening, this bucket might get 1 drip in it, and this bucket over here gets a drip in it, and then this bucket gets a drip, and then this one gets 2 drips, and this one gets a drip, and now this one gets another drip, and this one gets a drip. And as this rain falls on this array of buckets that we have out there, we have a sort of an imprecise collection method, right? Because raindrops are going to fall randomly into our buckets that we have scattered out there on our sidewalk. And eventually, over time, if it's raining out there for 20 minutes or an hour or whatever, eventually our whole sidewalk is going to be wet, right? But for a small measure of time, the number of raindrops that we get in any one bucket could vary a little bit, right? That's what shot noise is. Photons arrive at our sensor and impact each one of these pixels in a random way, right? The photons don't travel across the cosmos in a big straight line and all impact our sensor all at the same time. No, it doesn't happen that way, right? They sprinkle in, they get scattered in, much the same way as raindrops would be as they're impacting your sidewalk, right? So that fluctuation in the number of photons that arrive at a particular pixel is what shot noise is. Now, this cannot be prevented. This is, just the physical property of light arriving at our sensor. So there's nothing that we can do to stop shot noise, right? But we can minimize its effects in a couple of different ways, and we're going to talk about those ways, as we continue on here. But briefly, we can minimize the effects by having longer exposures and by stacking, right? Now, we're going to talk about how and why those things impact shot noise in a positive way. But understand that shot noise is typically our most significant source of noise in our photos. This is the big guy, right? This is what has the most impact, the highest level of impact on our images. Now, take my word for this one, because I didn't want to pull the proof out because I know I'd put you all to sleep. But shot noise increases more slowly than signal. In fact, the shot noise is equal to the square root of the signal. So as our signal goes up linearly in brightness, our shot noise will go up at a decayed exponential rate, right? Shot noise is the square root of signal. So if we see down here on this graph on the left, we see that as our brightness increases linearly, our shot noise first is keeping pretty good track with it, but then shot noise is slowing down more and more and more and more as our image gets brighter and brighter and brighter. If we flip this on its head and we plot shot noise as a percentage of signal, then we see a graph like we have down here on the lower right. And you see that as our image gets brighter and brighter and brighter, shot noise becomes less and less and less of an issue, right? Well, we all know this. Our stars, the center of our stars, are not noisy. Why? Because they're bright. And shot noise has been reduced because the image is so bright, right? But down in the little wispy bits of our nebulae, or down in the very edges of galaxy that we're trying to catch, or those little faint traces of dark nebula that we're trying to catch, that's where noise has the greatest impact, out there in the very dim parts of our image where all of the detail is. And kind of the bummer for us, the problem for us is that shot noise has the greatest impact where the signal is lowest, and it has the least impact where the signal is brightest. The core of the galaxy is not going to suffer from a whole lot of shot noise. The little wispy bits out on the edge, that's where the shot noise is an issue, right? So it's down in the darkest parts of the image that shot noise becomes more apparent. Does that make sense? Okay. So let's compare shot noise and read noise, these last two that I've been talking to you about. Let's suppose we had some hypothetical image where we had 3 electrons of read noise and 4 electrons of shot noise. How much total noise do we have? Do we have 7 electrons of noise? Do we have 1? Is 1 positive and 1 negative? Do we have -1? Do they flip around the other way? Do we have -7? Do they add in the negative direction? Well, the answer is yes to all of those, right? Noise is random. We don't know how it's going to come in. We might have 2 because one might, move a little bit more or a little bit less. So how much total noise do we have? How do we characterize that? Well, there's a really slick proof out there that we don't want to get into, but the answer is 5. Now, how does 3 + 4 = 5? Well, the 2 pieces of noise that we have, read noise and shot noise, add as the square root of the sum of the squares. Think of the Pythagorean theorem, right? If we had a little triangle, a little right triangle, and on the bottom we had read noise, and the vertical piece we had shot noise, the hypotenuse would be our total noise. They add up in the square root of the sum of the squares, right? Now let's take a more realistic example. I'm sorry. So there's our formula. The total noise is the square root of the sum of the squares of those 2 bits of noise. So if we had a brightness of 1,000 electrons, right? If 1,000 electrons were impacted by photons and were excited by photons and introducing current, we know that the shot noise, from what I told you back here, let's go back here. We know that the shot noise is the square root of the signal, right? So if we have 1,000 electrons in signal, we have 31 electrons in shot noise. The read noise, if we think back to our example that we had for a CMOS sensor, let's say the read noise was 1.5 electrons. The total noise is the square root of the square of 31 plus the square of 1.5. That works out to 31.65. Is it all that different from the shot noise? Heck no. Do we care about the read noise? My opinion, heck no. As the image becomes brighter and brighter, the contribution of read noise becomes less and less significant. It doesn't matter what our gain is. It doesn't matter where we're choosing to shoot, because that little tiny contribution of read noise is going to be insignificant when we compare it to what we're getting from shot noise. So in my opinion, the read noise becomes more and more of a non-issue. Just get brighter and brighter and brighter. I can already hear you guys disagreeing with me, but trust me, this is true. Okay.
Tim,
All right, we're going to move.
Question. There's a question.
Yeah.
Where,
Shoot.
Isaac asked, how is noise measured?
Well, how is noise measured? The read noise we know is measured by the number of electrons per pixel per second, right? Shot noise is the same thing. Shot noise is that variation from image to image in the number of electrons that we've collected for that pixel. And it's measured in the number of electrons per pixel per second. Does that make sense?
Makes sense to me.
Okay. As long as I convinced Eric, everybody else must get it. Okay. That was funny. You guys are allowed to laugh. It's all right. Okay. So we're going to come back to those things, but I just want to touch on these other bits of noise that we have that we're dealing with. Hot and cold pixels. I think we all know what these are. Basically pixels that don't work anymore, right? and a hot pixel reads white, and a cold pixel reads black. They either, read 100% or 0 or somewhere in between, but they're just reading a fixed amount no matter what happens with the incident light. That's what hot and cold pixels are. I think we all have a good understanding what those are. Fixed pattern noise is one that we might not understand so well. So we talked about what thermal signal was earlier, right? It's that little bit of current that gets induced into our photodiode in each pixel that we have in our sensor based on temperature, right? Now, raise your hand if you think that that thermal signal is going to be the same in every single one of these 6 million photodiodes that we have in our sensor. Heck no, right? It's not going to be the same. There's going to be variation from pixel to pixel in that thermal signal. The deviation from the average across the entire sensor is what's called dark signal non-uniformity, DSNU. Okay, so this piece of fixed pattern noise is based on the dark signal, and it's going to be the same from image to image to image, right? Because each piece of silicon will repeat itself in the same way. It just won't be the same as its neighbor. All right, that's what dark signal non-uniformity is: the variation, the deviation from the average on the amount of thermal signal that gets induced into each one of those pixels. Photo response non-uniformity, PRNU, is a little bit different. It says, look, if I have X number of photons impacting this photodiode, I'm going to generate a certain number of electrons. Will every single pixel generate the same number of electrons? Heck no, right? There's going to be a little bit of variation from photodiode to photodiode to photodiode in the electrical signal that gets created based on the same number of photons impacting that sensor. And that's what's called photo response non-uniformity. The deviation from that average is the PRNU. Is all that clear as mud? Yeah, you can't answer me anyway. I'm going to assume that you understand what I'm talking about. Okay. So those are two different pieces of fixed pattern noise. So what's walking noise? And Isaac, I think it was Isaac that asked the question earlier. This is where we're going to talk about. This is what we're going to talk about with banding or walking noise. Typically in DSLR cameras, mirrorless cameras, or uncooled Astro cameras, it's very challenging to shoot a dark that's the same temperature as what your sensor was when you shot your light. And in fact, the temperature of your light frame will change over time. Your camera's going to heat up, the ambient temperature is going to change, right? There's going to be variation because we're not controlling, the temperature of that sensor. So it's very difficult for us to take a dark frame and measure what that dark current is going to be, right? Now the noise is fixed. We already talked about that with the fixed pattern noise. It's always going to be the same for that particular pixel, for an exposure of that amount of time. But the star positions aren't, right? Float around on our images. We all know this. So as the star positions move around, that fixed pattern noise is going to move around in our final signal as well. And as we stack those things with star positions that are moving, that fixed pattern noise will appear to drift or band across the image. And that's what we commonly refer to as walking noise. And I stole an image off the internet of someone that was having some pretty significant walking noise. And that's what you see here in this image that I have in there as an example. You see that noise that gets striped and kind of strafed across their image as that as that fixed pattern noise moves with the stars. We see these bands of noise coming out in the image. So walking noise is really a manifestation of fixed pattern noise that comes out in our end image in different ways. Okay. All right. So how do we fight this stuff? What do we do about it, right? Well, there's lots of things that we do about it. Longer exposures help to reduce our shot noise, right? Why? Well, you should all know why. Because as our exposure gets longer, our image gets brighter. And as our image gets brighter, the noise increases at the square root of the signal. So as our image gets brighter, our shot noise is less, right? Or I should say, is less a percentage of our signal of our signal from our target object, right? The shot noise is climbing at a slower rate than the brightness of our image is climbing as we take a longer and longer exposure. It also helps to reduce walking noise because as our image gets brighter, we don't have to stretch this thing as much in order to get our target object signal to the point where it's visible. So we're not stretching that walking noise as much and making it as apparent. We're already talking about cooling the camera to reduce the amount of thermal signal. Of course, we still do that. That's still out there. We use dark frame calibration. We all know what that does, right? We take some dark frames and we use that to measure the dark current, the thermal signal that we have in the sensor when there's no incident light, and we use that to remove that thermal signal from our images that we've collected. It also helps us account for hot and cold pixels because we're going to see the same things in the dark frame that we see in a light frame. They'll still be hot, they'll still be cold in a dark frame just like they are in our lights, right? It also allows us to account for that dark signal non-uniformity, right? That deviation from the mean dark signal that we have across the whole sensor. The dark frames will allow us to account for that variation. Flat frames allow us not only to do things like account for the vignetting that we have in our image and the dust motes that we have on our sensor, right? That's what we all kind of think about flat frames for, but it also allows us to account for that photo response non-uniformity, right? Because we have incident light that's the same, if we do it right, that's the same across the entire sensor. And so if we see fluctuation from pixel A and pixel B and pixel C, we account for that with our flat frames when we do our flat frame calibration, right? Setting the appropriate gain on the camera to minimize read noise. I've already kind of said that's sort of small potatoes with modern cameras, but we're going to talk about that a little bit more in a moment. Dithering is another one. Dithering helps us reduce fixed pattern noise, right? Because we're constantly moving things around. And if we do enough of that, if we move things around with our dither enough in a random fashion, we're going to randomly account for that fixed pattern noise that we have both in dark signal non-uniformity and photo response non-uniformity. It also helps us to fight hot and cold pixels because those hot pixels aren't going to be in the same place every time. So as we dither around, right? We're also going to use it to reduce walking noise because it's doing the same thing that we talked about with fixed pattern noise, right? It's going to reduce walking noise because the fixed pattern noise is lower. Now, I would say that if you're using an uncooled camera, like a DSLR, a mirrorless camera, or an uncooled Astro camera, dither a bunch. Don't dither 2 pixels. Dither like 10 pixels, right? Move that sucker around so that we get that randomness and we start to average out that uncertainty. Okay. All right, now I'm going to get up on my soapbox. There's lots of misrepresentation, in my opinion, on what stacking is, because stacking is the next way that we're going to reduce noise or we're going to combat noise in our images, right? We all know this. We all know we use stacking, but why, right? And like I said, I think there's some misinformation out there where people represent stacking as adding images up. We're not adding images up. We're not increasing signal when we stack. We are averaging those images together. In fact, if you at the screen in PixInsight, you may have not even ever looked at it, but the combination method says average, or it says median, or it says min or max, but it doesn't say sum. If you drop this list down, it never says sum. It's averaging those pixels together, right? Now, there's lots of different rejection algorithms that we can set that throw outliers away. So all of those things like, if you're doing min max or Windsorized sigma clipping or percent sigma clipping or, all those things down at the bottom, those are throwing outliers out. If we have a signal that's out away from the rest of the norm, it throws those away. That's all that does, right? But it doesn't change the fact that we are averaging images together. We can also weight images differently, right? We can say this is a better image than this one, so consider this one more than we consider this. But in the end, we're still averaging pixels from many images together, not adding them together. And I think, you know, if you go out there and look around, you're going to find people that I think mistakenly say sum, and we're not summing anything. And that's important here. And I'll tell you why. Okay. So let's talk about why stacking helps us. Why do we stack? What the heck are we doing this for? Well, the averaging nature of imaging stacking reduces the shot noise, right? We're going to have a certain amount of shot noise in each image that we take, but that shot noise is random. If we take those things, average them together, that randomness of the error in shot noise is eventually going to fall out, right? And we're going to zero in eventually on how many raindrops were actually in our bucket, right? When we have enough readings, we're going to kind of settle in on the good measurement because the signal is going to stay. And the random nature of the noise is eventually going to average out, right? So the more exposures that we take, the more that randomness will tend to cancel out. Just like if we take a longer exposure, that randomness will tend to cancel out, right? So many exposures is really doing the same job for us as taking a longer exposure, but it's not because we're increasing signal. It's because we're driving the noise down. Our signal is staying the same, but the amount of noise that we have is being pushed lower and lower and lower because of this sort of averaging process. How much? Well, and how many should I stack? That's always the question, right? Now, this is actual data from a project that I'm working on right now, where I happen to have 200 luminance exposures. Now, don't ask me why I have 200 luminance exposures. It's part of this project that I'm doing, and you don't need to know why. It's not important. But what is important is the way this thing changes. So if we look here in the beginning, when I go from 1 exposure to, say, 10, my signal to noise ratio was changing dramatically. Remember, the signal to noise ratio is signal divided by noise, right? The signal to noise ratio. And it's a measure of how well we're measuring our target object signal, right? So this thing is going up drastically in the beginning, right? It's going up really quick. So from 1 exposure to 10, I went from, what's that, maybe 25, a signal to noise ratio of 25, up to, 33. And then from 10 to 20, I went from 33 to, I don't know, 37 or whatever it is here, 36. And from 20 to 40, I went to 40. You see it slowing down. And from 40 to 60, I went from 39 to 41. I'm not really changing that fast anymore. And from 60 to 100, I went from 41 to maybe, what is that, 43, 44? And from 100 to 200, with 100 more images, I went from 44. My signal to noise ratio only increased 1. As you combine more and more images, your signal to noise ratio change will slow down, right? And what I do to answer the question that I have at the top of the screen, how many should I stack, is I look at this signal to noise ratio each day as I've collected more images, and I look for that SNR to plateau. And once that number starts to slow down, I say, look, it's going to take me a whole heck of a lot more images to better this image that I have already. So I'm done at this point, right? I'm at the point of diminishing returns. If I go past 100 on this, it's going to take me a whole heck of a lot longer to make any significant change to the image that I have. So the answer to how many should I stack is going to be different for every target, but you can zero in on it by looking at how that signal to noise ratio is changing as you continue to gather data. And when you see that sucker slow down, you know you're done. Right? Makes sense. All right. So the next question everybody asks is, how long should my subs be? And I took this from a presentation from Dr. Robin Glover. I agree with this part of his analysis. I don't agree with where he goes with it after that. But the part that I agree with is here. And so let's assume that we have read noise of R and a total imaging time of T. For my examples here, I used an hour. And a sub-exposure length of whatever it is. The number of subs is going to be the total time that we have divided by the number of subs. That's N. And our light pollution rate is P. Right? The number of electrons that we have due to light pollution is the time, the sub-exposure time that we have times that light pollution rate, or S times P. The single frame shot noise from light pollution is going to be the square root of that number, right? We know the shot noise is a square root of the signal. Yes? The total noise that we have from light pollution is going to be the square root of our read noise squared times the square root of S and P squared, which is S times P. Right? And the total noise for our whole stack is going to be the number of exposures that we have times the read noise, plus the number of exposures that we have times S times P, or T times P. That's going to be our total stack noise. Right? So, all right, all these equations are kind of boring and don't really tell me anything. What do you mean, Tim? Well, here's what I mean. Let's look at total stack noise versus sub length for a fixed exposure time, let's say 1 hour, okay? And let's look at different sub-exposure lengths with a sensor that has 1.5 electrons of read noise and one that has 3.5 electrons of read noise. Well, you see what happens here is that if we take a 3,600 1-second exposures, our noise is going to be here, what is this, around 90 something, right? If we have 2-second exposures, so what's 3,600 divided by 2-second exposures, it's a little less, and 10-second exposures is less. But you notice when we get down here at around, what is this, 20 seconds, 30 seconds. From 30 seconds to a single exposure of 3,600, which would be our best when we're talking about noise, total stack noise, right? That number didn't change. Right? It didn't get any better when we're talking about sky brightness and the noise that we're seeing from the sky from a 30-second exposure here when we have 1.5 electrons of read noise all the way out to a 3,600-second exposure. With 3.5 electrons, it takes a little longer, but it does the same thing, right? If we get out here around, what is this, a little less than 120, let's call it 118. If we're out here around 118 seconds, it's not going to get any better if we go all the way out to 3,600 seconds. Note that this is a logarithmic scale down there, folks. So there is a point that from a noise perspective, our longer exposures don't help us from a noise perspective. And remember that I'm putting that caveat in there that says from a noise perspective. Now let's look at it a couple of different ways. Let's look at the relative noise. So we're going to compare this to our total noise at the end based on sky brightness, right? Notice that our Bortle 7 guy that's shooting this in the city pretty much doesn't get any better after, what is this, 8 seconds than he does going all the way out to 3,600 seconds. Our Bortle 4 guy has to shoot until he gets out here around, I don't know, a little over 100, maybe 110. Our Bortle 2 guy has to go all the way out here to around, 300, maybe 300 seconds before he's, got to within a small percentage of what it ultimately will be. Now, this graph kind of lies to us and makes us think that we're getting to the same point. We're not, which we're going to show in the next. But remember, this is relative to what our final image would be, right? So I'm dividing this by the final noise. So the darker skies require us to shoot longer before we get to that same point. Now let's look at what that final noise will be. And for right now, I'm going to ask you to just graph on the left. This is 1.5 electrons of read noise, a Bortle 7, a Bortle 4, and a Bortle 2 sky with an f8 scope. Okay? Notice that the same thing that we talked about earlier, the Bortle 7 guy, you know, he's done after 30 seconds or so. He's not going to get any better when it comes to read noise, or excuse me, when it comes to total noise with respect to sky brightness. The Bortle 2 guy has to shoot much longer. He has to come out here somewhere before he's really getting to the same point. All right, now I'm going to ask you to look at both graphs, because notice that no matter if our read noise is 1.5 or our read noise is 3.5, or trust me, it would be the same if I did 7 or if I did 25 electrons of read noise, given enough time, we get to the same value. This goes back to the statement that I made earlier, that when you consider read noise and shot noise, as our exposure gets brighter, i.e. as we take a longer exposure, our read noise becomes less and less significant. Here, it's not changing our final number at all, right? But anyway, the takeaway here is not so much about read noise, but more about what our minimum exposure needs to be, right? Our minimum exposure for the guy in a bright sky is not going to get any better because of the light pollution that he has, whereas the guy shooting in a dark sky has to expose for longer so that he can overcome the noise from the sky brightness. It's almost counterintuitive, right? A little freaky.
Tim,
Sir.
a couple of questions.
Actually, can I ask you to hold them for one more slide,
sure.
and then I'll answer them? All right, one more slide. So let's look at one more thing here. As long as we're talking about this, let's look at total noise by filter, right? Now, why is this different? Well, the amount of light that we're getting through the filter obviously is different, right? And that almost has the different level of light pollution. So all of these are for an FH scope in a Bortle 2 sky. And I chose a Bortle 2 sky just because it was more obvious than it is in a Bortle 7 sky. But if we look at a Bortle 2 sky, we see that our luminance kind of settles down quicker than RGB, and RGB settles down quicker than narrowband. And out here, I've given the numbers. If I look for when the frame is within 5% of a 3600 second exposure, the luminance gets there in 135 seconds. RGB doesn't get there until 380. And narrowband doesn't get there until 1680. So we have to shoot longer to get to the point where we've completely minimized out that noise due to sky brightness for a narrowband filter than we do for an RGB filter, and for an RGB filter than we do a narrowband filter. All right, Eric, shoot me with your question.
Okay. Let's see. Josh asks again about someone writing a PixInsight script to calculate it based on the subframes of the camera. Is there a script in PixInsight that goes through that calculation?
That calculates what?
The one you showed 2 or 3 slides ago.
This one?
Yeah.
I don't believe so. I'm not familiar with one, but that's not to say it doesn't exist. There are lots of scripts out there for PixInsight that I don't know about.
Okay.
Now, what there is in PixInsight that I use all the time is a script that shows you what your signal to noise ratio is on your stacked image, and that's something that really gets to the heart of the matter. That's really what we're doing. The reason that we went through this analysis is just to see what we need to do with exposures based on light pollution, filter that we're using, focal ratio of our telescope, all those kinds of things.
Okay, John asked, can Tim explain how they, he's referring to Bray Falls, can pull ultra-low O3 signal out over sky brightness like the M31 and oxygen arc?
Yes, I can explain it.
Okay.
And I think if Bray were here, he would tell you the same thing. Long exposures to get a little bit of brightness in that image, because we've got a very weak signal, right? So we need a long exposure before that thing starts to come out. Number 2, lots of image in the stack. Why do we need lots of images in the stack? Because of what we talked about here. We need to drive that signal down, right? So we have a very weak signal from oxygen, right? So we need to drive that noise down as much as we possibly can in order to bring that signal out. So we lengthen the exposure in order to make that signal as bright as we can. And we're going to talk about that in a second, but we lengthen that thing to make that signal as bright as we can. And we take lots and lots of exposures to drive the noise down. Now, I've already shown you that lots and lots of exposures is good. It really is lots and lots of exposures, because in order to drive it down past a certain amount, we have to take a ton of exposures, right, to drive it down any further. So what Bray and what I forget what the other team is that are doing all these, discoveries with PNs and whatnot. I've forgotten their name. But anyway, what they're doing is taking lots and lots and lots of exposures across many astrophotographers, across many, many nights, with long exposures, to try and do everything that they can to drive the noise down and bring out the faint signal.
So I have to ask on that last graph, why did you go from 100 to 200 subs?
Why?
You were already there, weren't you? You were already mostly on the plateau.
So this is the project that we're working on, Eric. Where again, this is another project that I'm not going to talk too much about, but that Eric and I are working on with a bunch of other astrophotographers, where we're trying to bring out some very, very weak stuff. And so there's a group of astrophotographers out there, a whole mess of us, that are all shooting a ton of exposures in the same piece of sky to try and bring out some very, very, very faint signal. So that's why. For my own images, I would never do this, right? Unless I was trying to get something that was very faint.
And Chris had a question, but I think he says it's already been answered. So we're good.
Okay, good. So this, to me, is a very important slide, and one that should be important, I think, to all of you, is that not necessarily what the exact numbers are. Forget about the exact numbers, but the fact that whatever our luminance exposure is, wherever we think we're getting good luminance, our RGB exposures need to be at least double that for red, green, and blue exposures. And our narrowband exposures need to be, at least 10 times that before we're getting to the same level of noise induced by light pollution, the atmosphere, sky brightness, all that other kind of stuff. All right. So let's talk about my thoughts on exposure time. And this is, like I said, this is my thoughts. This is what I think, right? And I think that this exercise gives us a good idea of how we can think about what our minimum exposure should be. Not so much the number, but the method, right? Think about what our minimum exposure should be for luminance, and then subsequently RGB and narrowband as well, right? But what doesn't it do? Well, it ignores the brightness of the target object, right? It doesn't even think about that. It doesn't even consider the brightness of the object that we're taking. And it doesn't even consider the dynamic range of the chip, which is finite, right? These sensors, remember, these are digital devices. They are not analog devices. They don't have an infinite dynamic range. They have a very, very finite dynamic range. So setting things for our minimum exposure probably isn't the best, right? So I'd say use this for an idea of how small we should be, but really what we should be considering when we're thinking about how long our exposure should be, we should be considering the full well depth of our sensor and the brightness of the stars in our image and our ability of our mounts and guiding and everything else to track that bit of sky for a certain period of time, right? That, to me, is much more important than the exercise that we just went through to figure out how noise is impacting our image, right? We need to make sure that we're above those minimums. But the real question is, how long can I go? Because remember, the longer we expose, the greater impact we have on our shot noise for every single frame. And then as we stack those frames, the better we're going to be when we're trying to drive that noise down away from the signal that we've captured, right? So in my opinion, I do not follow the advice of some that suggests that, hey, these CMOS cameras are so great that we can take really short exposures and get a great image. You can get an image, but I humbly suggest that you won't get a great image, right? And the better images will come when we make that target signal as bright as we can to drive down that shot noise, which again is our big guy. And the more of those that we stack, the more we drive that noise away from that signal.
Tim, can I
Now-
add just one comment here?
Sure, of course you can.
About the length. Something, I mean, it has nothing to do with noise, but I like to look at how many stars are being blown out on my image, especially on RGB. Because even if you say, well, I should go longer, if you blow out all your stars, you got no color. in
Yeah,
your stars.
that's what I'm saying in this point right here. Consider the full well depth of the sensor and the brightness of the stars. You don't want to all of a sudden be pushing all of your stars into saturation because you're out of full well just to take a longer image to increase the signal of the nebula, for example, right? So you have to consider what the full well depth is of the sensor and the brightness of those stars. And in my opinion, push that gain down. Push the gain down so that you don't push your stars out of the full well depth range for your sensor, right? We already proved a few slides ago that we don't care what the read noise is. So push the gain down, expose for a longer period of time, make our shot noise average, let our shot noise average out over each pixel that we have on our sensor and expose for longer. Right? Okay. So why don't I think we should do a bunch of short exposures? Well, I think you already kind of get it, but you know, space and processing time are negatively impacted. We know that. That's simple, right? But as I said already, your camera doesn't have infinite dynamic range. So if you have a little teeny tiny signal like this that you try and stretch, what's it going to look like? Well, you've taken that little teeny tiny signal of a couple of ADUs and stretched it over a whole bunch of ADUs. It's going to look blotchy. That's where you get this mottled kind of blocky look that you see in some images, right? When there wasn't enough signal and they've stretched it too far and it starts to look blocky. You need to increase that amount of signal that you've captured so that when we do stretch it, it still appears to be smooth, right? Got to remember, these are digital devices, not analog devices. I can take an analog signal and with a perfect amplifier, which doesn't really exist, but with a perfect amplifier, I can blow it up and it'll look exactly like the incident signal, just bigger, right? You can't do that with analog. The more that, or excuse me, you can't do that with digital. The more that we stretch that signal, the more stair-steppy, the more blocky it's going to look because we just don't have the resolution, right? Also, you'll dramatically increase the shot noise in a single image with a short exposure. We've already shown that, right? In shorter exposures, the image isn't as bright, so the noise is much higher. The shot noise is much higher than it is in an image that gets brighter, right? So we have to give those raindrops more of a chance to find our buckets and average everything out with the longer exposures. Now, just for fun, last night I took my rig out at the SRO and I shot these are luminance images. I shot 120-second exposure all the way up to a 1200-second exposure, and I don't know if they're coming through well in YouTube. I know the picture can be quite small, but I can. But if you can see it, you'll notice that this image is much more grainy, much more noisy than this image, right? Each step of the way from 120, 300, 600, 900, 1200 seconds, all of a sudden at 1200 seconds, this sucker's starting to look nice and smooth. And I've got lots of detail that we can see here that I just didn't have before, not because the signal is lower, but because the noise is higher, right? And remember what we saw way back in the very first slide, the more noise that we have, the less fine detail we have come through in our image, right? Because that noise obscures that fine detail. And you can see here that I've got much more fine detail in the core of this galaxy. This is M101, obviously. Much more detail in the core of the galaxy than I even have at 900 or even falling down to 300. Look at the difference from here to here, right? This is all because these are all single exposures. I didn't do any dark frame calibration, no flat calibration, nothing like this. This is straight out of camera. But you can see that the image here and the image here are vastly different just because I've reduced that shot noise with a longer exposure. I mean, I hope you can see it. I hope they come through on what we're looking at in YouTube. And that's all I got. So I know we just answered a bunch of questions. Do we have any more? Sounds like no. No more questions?
I don't know where Eric went, but there's a couple more. Let's see.
Shoot.
You want to talk about dark frames a bit with the newer CMOS cameras? Not necessarily, but some argue that you don't really need dark frames as much anymore with the lower noise on the newer cameras. What's your take on that?
Well, I would say that the importance of dark frames for CCD cameras was much greater. Because why? Because the dark current was much higher, right? So is the impact less? Yeah, I think the impact is less. But don't forget, we've got dark signal non-uniformity to deal with. We've got that fixed pattern noise. So even though the total amount of noise isn't really that high anymore, we still have that fixed pattern noise. And if you don't want to deal with that fixed pattern noise as we stretch this image up, ultimately, we've got for it somehow. And the way that we account for it is with dark frames. I can tell you, I shoot with CMOS sensors and I still do dark frames on every image that I do.
Is there a different consideration for if you have a high level of light pollution versus little light pollution in the impact dark frames will have?
I'm sorry, ask that again, Molly.
Does being under light pollution or not make a difference in how effective dark frames are for you?
Yes. Well, I mean, we saw that earlier, right? Because light pollution is going to add in, let's say we're in a place where light pollution is adding in 4 electrons of noise and our dark frame is only, our dark current is only adding in, 0.01 electrons per pixel per second of noise. Does it matter a whole heck of a lot? Yeah, right. Exactly. It becomes less important as the amount of noise from other sources goes up, right? And light pollution is a big one of those. So yes, the importance of it wanes, but I can tell you that I still do it on every image that I take.
Yeah, same. There's another question here again from Josh. So are you saying we don't need to care about unity gain?
You absolutely do not need to care about unity gain. In my opinion, unity gain is a convenience for people that don't really think about what gain is doing, right? The only thing that unity gain does for us is allows us to say, well, 1 ADU equals 1 electron. Well, who cares? I don't care, right? Now, what we really care about is the amount of read noise that we get based on gain and the amount of signal that we get based on gain. So I'll tell you from my perspective, the only reason that I increase gain is because when I'm shooting narrowband, first of all, I know I'm never, ever going to fill up the full well. And I don't care about stars in narrowband, right? So there, I can increase the gain, turn the gain up a little bit to make sure, to allow me to shoot a shorter exposure and get something that's brighter, right? When you're dealing with sulfur, I don't want to sit there and do an 1.5 hour exposure, right? So I'll push the gain up to allow me to shoot a shorter exposure and still get some signal. But really, that's all that we're doing. I don't care what the relationship is between the number of electrons and the number of ADUs that I have. I don't care. So there's no real reason, in my opinion, to care about unity gain.
Does that calculation change if you're doing a high dynamic range target like the Orion Nebula or the Ring Nebula?
If you're doing a high dynamic range target, you want to push that sucker so far below unity, as far down as you can, because you've got really, really bright stuff, right? So that really, really bright stuff is going to blow out if you push the gain up towards unity, right? You want it to be lower so that you have a better chance to expose long enough to get some signal, because, remember, I skipped a step here. Let me back up for a second. Remember that as we push the gain up, our full well drops, right? If you look at your full well on any of the cameras that I've ever looked at, the full well comes down as the gain goes up, right? So if, let's say, your full well starts out at 52, at a count of 52,000, right, with a gain of 0, you push that thing up to unity, and it's probably half of that, if not less, right? So if you have a high dynamic range target, all of a sudden you've chopped the length of exposure that you can do way down, because those bright areas of M42 are going to get blown out so fast because you don't have the full well depth anymore, right? You want to be able to get that big difference between the really bright stuff and the really dim stuff. And the only way to do that is to push the gain down away from unity where you have the full well depth.
Or in this case of M42, to shorten your exposure way down, which is
you can do that, but what's going to happen? Shorten your exposure way down, we have less signal. We have less signal, we stretch it up. Now all of a sudden we're getting blocky, like I was talking about before, because of the dynamic range of the chip.
And then you need multiple exposures. And with M42,
multiple exposures will not cure blocky images, no matter what you do. Right? If they get blocky, it's because you're stretching it too much and you don't have enough signal. And it doesn't matter, because we're averaging. You don't have enough signal, average more of it. You still don't have enough. It doesn't matter.
I guess M42 is a particularly unique target.
Right.
So there,
well, even for like Ring Nebula, if you're going for the dim secondary outer ring around the main ring, or a lot of planetary nebula that like Cat's Eye and stuff like that.
Right. So the problem there when you're going dim, and this is another reason why, just like my narrowband example, this is another reason why you play with gain, right? You have something that's really, really dim. So what are you going to have to do to get enough signal? Well, you're going to have to expose for a long time if you're at gain 0, right? And exposing for that kind of time makes guiding more complicated, makes, you need a better mount, all these other kinds of things, right? All of that stuff gets more difficult. You have a greater possibility of a satellite coming through your image or an airplane flying through. All of those problems come in, right? So when you're doing something that's really dim, and that you would consider pushing the gain up, is so that you can shorten the time that you're taking that exposure. And again, if it's really dim, the dynamic range isn't as much of a problem. You don't need as much if the whole thing's dim, right?
Well, I guess what I'm saying is like you've got the center part of the ring, for example, that's very bright, and you've got the outer ring that's very dim. You have to kind of balance those two.
You have to balance that.
Right?
Exactly. Right. Exactly.
There's a question I missed earlier about, so the question about banding was more referring to not the walking noise banding, but the banding that's inherent on some sensors, like some of the Canon sensors and stuff like that. They're asking about like, what do you know about the cause of that banding?
Very, very little.
Okay.
Very, very little. Sorry.
We actually have another banding issue with that big sensor that we use. Remember how it's split into 2 parts?
Well, that's not really banding. That's that's 2 separate pieces of silicon.
Right? Silicon.
Yeah. So with that IMX 455 sensor, there's 2 different pieces of silicon, right? And so, great example, Eric, of two different sets of photodiodes that are behaving differently, right? And because we're on 2 different halves, we see that difference in a seam right down the middle of the raw image, right? How do we deal with it? Darks and flats. Darks and flats get rid of all of that mess and bring that image into a nice homogeneous, because we're accounting for the differences in those 2 different halves of that sensor.
And I can tell you that it doesn't always work well. It doesn't work.
You're just not good enough at it. That's all.
That could be. On a very dim image, when you start second, the flat doesn't get rid of that issue on occasion.
Dark. the dark.
For the YouTube record, sometimes banding on images, with the exception of some sensors that band for some reason, sometimes it's actually just a USB issue. And especially if the banding is random and not fixed, looking at the USB traffic setting, especially on CWO cameras, can help fix that issue. Just to toss that one out there, that's not entirely related to this talk.
Thanks, Mom.
Let's see. So what else? Isaac wants to know what is RMS and how does that relate to noise?
RMS means root mean squared. So the square root of the average of the squares. So you take all of the measurements that you have, you square them all, you average it together, and you take the square root of the whole thing. That's all RMS means. So it's a way to express a measurement that engineers use when they're talking about things like noise. So if you have a certain number of electrons, RMS, that's really all they're talking about. What is the square root of the average of the squares of the noise? That's all that is.
He also asks, what about quantization noise?
Quantization. Okay, so quantization isn't really noise, but error, right? So I told you that we're converting this analog signal into a digital signal, right? And sometimes if we have 0.1 volts, it might turn into 1,000, and sometimes it turns into 998, and sometimes it turns into 1,002. That little tiny difference there is quantization error. Where does it come from? Well, remember that we're measuring that signal for a finite amount of time, right? And we have a random number of raindrops hitting our bucket. So we take this fixed amount of time and we say, count the electrons in here, and we take a reading, and we count them again, and we take a reading. That difference in converting that analog signal into digital and going from that infinitely responding analog signal into a digital signal is the quantization error, right? And it's just a manifestation of taking this analog signal and turning it into a digital one. It's not noise, but error. Now, you could say it is noise because it has the same effect. Well, yes, it has the same effect, but it's not physically, it's not really the same thing as noise.
I know we're running long, but we seem to have held our audience pretty good. So
Yeah.
We are running long. I did this in 30 minutes.
There's another question here going back to the earlier discussion about exposure time and gain. So Chris wants to know, so the bottom line is essentially take longest exposures at lowest gain possible and stack as many as possible, or maximize dynamic range and exposure length, basically.
So yeah, so it's tough to give you a single answer that covers all the bases, right? So in my opinion, that's not far from the best answer. But as I said back in that slide, maybe I should bring that back up again. Let's bring that back up again here. Hang on one second. And I'll try and give you the bottom. I'm sorry, who was this question from again, Molly?
Chris Kagi.
Chris. So what you really should do is think about the full well depth of your sensor and how bright the stars are. This is the first thing that I do when I'm trying to set the exposure time for a new target, right? Is Betelgeuse in the image? Well, if Betelgeuse is in there, that sucker's pretty bright. Is Sirius in there? Is Polaris in there? Is something really bright in there, right? Then I'm probably gonna push that exposure time down, right? But that's what I really do is I consider the full depth of my sensor and how bright the brightest stuff is, and try and set the exposure in there. Now, typically, what gain do I use? Well, I have the Moravian C3 camera, which has that IMX 455 sensor, the same one that's in the ZWO 6100, lots of them, right? So that's the sensor that I use. Personally, I like to push the gain down so I have more full well depth, right? So I shoot at 0 when I'm doing broadband. And the reason that I do that is to get that huge full well depth, right? Now, I don't mind shooting a 5-minute, 10-minute, 20-minute exposure. It's fine with me, right? I'm okay with that. So if I can push that gain down to 0 and shoot a 20-minute exposure and have all of that well depth, have all of that dynamic range, I'm in high cotton, right? That's what I dig. Now, when I start shooting narrowband, and all of a sudden I have, 3 nanometer, a 3 nanometer band pass versus 300. Well, okay. All of a sudden, my single exposure is going to have to be really, really long if I shoot that sucker at 0, right? So even though I like to have all that full well depth, when I'm shooting narrowband, I push the gain up so that I can get my sub exposure down to something that's a little bit more manageable, right? And I usually shoot a half an hour exposure when I'm talking about narrowband. So, that's typically where I go, and I'll adjust the gain up to the point where my read noise drops, and that's usually where I shoot it. So when I say in these two statements here that are, can I highlight these? I don't know. No, I can't highlight them. Let me get back to that. But when I talk about these two statements that I have, right here, consider the full well depth of your sensor, the brightness of the stars, and consider the ability to mount of your mount and guiding solution to track. That's what I'm talking about. That's what I look at when I'm trying to figure out how long for this target I want my exposure to be. I want the most full well depth that I can have so that I get that big difference between the really bright stuff and the really dim stuff. Does that answer the question, Molly?
I think so. Hopefully we'll see if he comes back with another comment. I think, yeah, he did say that there's not enough room in the chat box to kind of get to the more subtle parts of that discussion, but hopefully that kind of covers it.
Okay.
Isaac has a couple more questions. Should flats be at the same gain as lights?
Should flats be at the same gain as lights?
Yeah.
Myself, I always shoot flats at the same gain as lights. Doesn't matter is the question, right? That's really the issue. It doesn't matter. I would say that the textbook answer is it doesn't matter because the percentages are going to be the same when you're dealing with flats. But in reality, we're dealing with imperfect pieces of silicon here, and I want the response from the photodiode to be the same for that fixed pattern noise in my flats as it is in my lights. So I always shoot them at the same gain. So for me, I say shoot them at the same gain.
I suspect you might get the issue of where flats appear to overcorrect if the gain's not the same, but I haven't tested that myself.
Yeah. So, personally, that's what I always do is shoot them at the same gain. Same with the darks. Obviously, you want the darks at the same gain because your thermal signal is going to vary based on that gain as well. So I always shoot the darks at the same gain. I shoot flats at the same gain. And I shoot sky flats in my rig. So that's another good argument for me to shoot them at the same gain is because I'm essentially taking another light just with a different target and using that as a flat.
Except you're taking them at 30,000 ADUs across the face of the chip, not 500.
Right.
I mean, I shoot them at the same gain, but I don't think it would be absolutely necessary. It shouldn't make any difference. If you're at the linear,
that's kind of what I say.
If you're at the linear part of the response,
that's right. If you're exactly right, Eric. If you're in the linear range of the chip, it's not supposed to matter. I don't know. I do it at the same gain.
He also asks about bias frames. Do you need bias frames? And if you do they need to be also the same gain and offset as the lights?
Yeah. So let's talk about bias. So bias is something that we had to do when we were dealing with CCD cameras, right? But when we moved over to CMOS sensors, it became more difficult because they don't have a way to do a 0-second exposure. What is bias? So maybe we should start with what is bias. Bias is the signal that is inherent in the chip in a 0-second exposure, right? But they're in CCD cameras, most of them, we could take a 0-second exposure and get a bias signal. In CMOS, we can't. Does that mean there's no bias? No, of course there's bias, right? There is bias in a CMOS sensor, but there's bias in everything that we take. So when we take a dark frame, there's bias in it. When we take a flat frame, there's bias in it. When we take our light frames, there's bias in it. So how do we account for bias in a CC camera where we can't take a 0-second exposure? Well, we use something magical called flat darks, because your dark frame, remember, is going to subtract the dark signal and the bias signal out of your lights, right? The problem is the flats. The reason that we took bias in CCD cameras was for the flats. So how do you get the bias out of the flats? Well, you take what's called a flat dark. You take a dark for the same exposure as what your flat was taken for, and you subtract that flat dark from the flat frames, and that will take out the bias that's in the flats as well. And now you've got a light with no bias and a flat with no bias that you can calibrate. So bias, you are accounting for it, but you're accounting for it by taking a dark frame for your lights and a flat dark for your flats. Is that clear as mud? Did I explain that well?
Yeah.
Okay.
And Pix Insight will do a lot of that automatically for you.
Well, it does it all automatically. You just have to shoot it, right? You just have to make sure that you shoot flats at the same exposure length as your excuse me, you take darks at the same exposure length as your flats. For your dark flats, you take darks at the same exposure length for your lights to calibrate your lights.
And that can be a little tricky if you're doing sky flats where the lightness varies second by second.
Yeah, it can. And what I do when I shoot sky flats, I usually shoot 20 frames, and I look at the longest exposure and the shortest exposure, and I try and hit the middle. That's how I do it.
Yeah, it's a little easier when you have a flat panel.
Yeah.
I know we're running long on time. And there's some more notes that kind of discussion points here. I guess I'll just have one more here, and you can decide how much you actually want to answer this. But
Okay.
what about the offset setting? I know it's like a whole show unto itself, but
Yeah. The offset setting is I will confess to having imperfect knowledge of offset. My understanding of it is we want to get it up high enough that we get a baseline that's above some of the non-uniformities in the lower end of the chip. Frankly, the camera that I use, that offset is fixed. And, I think, for most of us, if we throw in a number that's, that's around, I don't know, what do you use, Molly? You shoot a lot of ZWO cameras. You throw in an offset of like 50, 75.
10 for some, 50 for some. From what I've read, 'cause I wrote an astronomy article about this not too long ago. From what I've read, there's a sufficient offset, but there's no ideal offset, basically.
Right.
And there's some math you can do to determine what your sufficient offset is. But really what you're trying to avoid is subtracting pixels when you do your dark subtraction that make it go below zero, basically.
To push into zero. Right. Yeah. So throw an offset in there that gets you above some minimum, and check, when you take your frames, make sure that you don't have after you do your calibration frames, make sure you don't have pixels that are zero.
Yeah.
And if you don't have zero, your offset's probably sufficient. Like you said, Molly, we could talk about that probably for a while.
Yeah. There's some websites that kind of go through how you can figure that out for your camera, stuff like that. But I just use the default, and I haven't had issues with dark pixels. And if there are, it comes out after registration anyways. So it gets written over with dithering. Okay. I know there's probably some other questions and discussion points in here that people would love to hear about, but we are running log on time. We should they've slowed down at least. So
okay.
We can probably, I guess one parting shot. Do you create dark libraries for
I do.
temperatures, exposures, etc.?
Yeah, I do. I take, and I have a script. I personally use Voyager, and I have a script that I run in Voyager that takes, a certain number of dark frames at exposures, in different increments. And I try and zero in on those increments of exposure whenever I'm setting up a new target. And I have a library, dark frame libraries I reshoot every year. I don't think they change much. Flats I reshoot every 3 months, and that's not even necessary because I don't see a lot of change. Because my rig is together and it stays together. So my flats aren't really changing all that much. If you're setting up and taking down every day, every time you shoot, then that's an argument to take flats every time that you set up. But for me, my rig gets put together and stays together, so I don't really need to shoot flats all that often. So I have libraries both for my dark frames and for my flats.
Yeah, with regard to go ahead.
If you have an open telescope, you're taking flats more frequently, not darks. So every time a cigarette burn shows up, new flats.
Right.
Yeah, with regard to dark capture frequency, I have found that about every 18 months on average for my sensors. Yeah, I don't know exactly what it is, but something the sensor changes over time. I don't know if that's due to breakdown or use or heat or what, but my darks stop working after a while. Like I'll do a dark subtraction and the whole image will be black, wherein it wasn't a year ago. And so I find about 18 months is about when my CMOS cameras need new darks.
Yeah, I mean, I don't know this implicitly because I although I am an electrical engineer, I never built silicon, but I would suspect that over time the properties of that photodiode are going to change. And like I said, I reshoot mine every year just because that's what I've done since I started and it works. And so I didn't argue with it.
Yeah. Okay, I think we'll probably call it there. I do want to point out that we have a lot of openings in our calendar, if y'all have been looking at our calendar, and we really need some speakers. We go out and we ask folks that we know and we've met to come on and talk, but sometimes we need some folks from the audience to come volunteer. And yeah, we've been on for almost 10 years now, and we've covered a lot of topics, but as we've said in the past too, everybody has a different perspective on a lot of these different topics, or a solution to a problem that's different from somebody else's solution. And if there's something that you would like to come on and talk about, whether that's hardware related, is there a cool device you're using? Like we had somebody come on and talk about what an atmospheric dispersion corrector was. If there's like maybe you've been using a less common processing software like Astro for planetary processing, or what's the other one besides PixInsight that a lot of people use? There's like Cyril or Astrophoto, AstroPixel processor. If you've got some cool workflows or processes in those that you want to share with folks, we have a lot of PixInsight topics, so it'd be kind of cool to get some of the other softwares that people sometimes use, or all variety of things. Send us a note on the contact us page on our website, theastroimagingchannel.org, and we'll see if it's a good fit. And yeah, so go and reach out to us if you'd like to come present, or if you know somebody, you can ask if they'd be interested in presenting as well, and send them our way. Yeah, we need some folks to come fill in our slots. And I think with that, we will call it a night. Thanks, Tim, so much for that great discussion. It's a lot of useful information that people really need to know and are obviously very anxious to know about, given all the discussion tonight. And yeah, that was great. So thanks.
Thank you, everybody, for your attention. I appreciate you being here.
All righty, we'll call that a night. Take us out.
Bye.